Yeah, I will start. So you some questions?
I had a question.
Yeah.
What the definition of the IPC says? How does one think about it?
You mean to say how you define?
How is it defined?
Basically, ITC is set by the tropical convergence zone. So if you really see the wind pattern over tropic, in the northern hemisphere it's all northeasterly, and southern hemisphere is all southeasterly. In some place, somewhere it converges together.
So that line of convergence?
Yes, it's a line where you get a lot of precipitation. Large scale convergence, then large scale ascending motion, then a lot of rain. So rain is basically maximum cloud zone we call. So that's a place where it rains. And that is the region where all tropical cyclone forms. So a small, what is
Typically a line like
is a line like this.
that moves upward. With
It moves upward, sometimes it goes down. Southern hemisphere, in the winter season, for our winter season, it goes down. In the summer season, it goes up, and over the monsoon region, it comes, then we call it a monsoon. So Pacific also, it goes north. But it's not, in the Atlantic, it doesn't go north. It is almost like a stationary. And this is where ITC said all tropical cyclones forms in the ITC region. ITC set. A small vortex forms there, then it moves, it gets intensified through some mechanism, so what we call instability mechanism, then it grows. Yes? Yeah, there is a region, I saw it called ITC is a region, nothing but east-west orientation of the convergence zone, and tropical cyclones form the convergence zone. As a small vortex first is formed, then it gets intensified through mechanism, different instability mechanisms are there, and once it grows, then it grows beyond this thing, variability, natural variability, then it becomes a cyclone. Then it moves north. It gets dissociated with ITC set. ITC set will stay there, but this one will start moving it. Any? It is starting from ITC set. What was?
So I think there is mathematically a theorem that there must be a vortex somewhere in the 276. Why is it that they preferentially form in that region? I think
Preferably forming over the region. That is a region of convergence. So yeah, vortex can form only over that region. And once ITC set moves north, then because you need a shear to rotate, isn't it? You need a shear to rotate the vortex. So you need first of all, a convergence that can be trigger a vortex, and the vorticity can really form from the. And it forms off the equator. It doesn't form near the equator. So when I showed that ITC said one in the southern hemisphere, one in the northern hemisphere, you would have noticed that equator is free of any clouds. So a cyclone cannot form over the equator, mainly because the Coriolis force is zero there. You need a Coriolis force to rotate it. So Coriolis force is nothing but 2 omega. Coriolis force is nothing but 2 omega sine phi. Omega is the Earth's rotation, 2 omega sine phi. Sine phi is 0 there, so sine phi is 0, so you will get Coriolis force 0. So it starts somewhere around 10 degree north and 10 degree south. So Coriolis force is a major factor to trigger the vortex. Okay. So shall I go to the next one? So this is a part 2. So question is, many people talk about the weather and climate almost like a kind of a same bag. It's not so. Climate is different, weather is different. And so weather is instantaneous, what you experience. Climate is a kind of a long-term mean. So basically climate is what you expect, but what you get is weather. weather is what you get. So for example, Bangalore is climatologically, climate-wise, it's good. But on a particular day, your weather can be very nasty. Okay, it can give rise a lot of flooding and all these things. So now question is how you predict. So how you predict? There are many ways you can predict. I'll start with persistent climatology. Today's temperature is 25. Assume that tomorrow also it will be 25. So that's one way of prediction. Okay, and so persistence for temperature, it works very well. But it doesn't vary that kind of, it doesn't have that kind of variation, day-to-day variation. Climatology is not used for temperature, but it can be used for rainfall. For example, you can say that over Sonipat, next monsoon season, you can get the same amount of climate value. For example, 25 centimeter, you can get 25 centimeters. Some people are online. Okay. Okay. So the second is analog. For example, a particular event has happened. So next day, so like for example, a monsoon depression came and they gave a lot of good rains. So for the forecaster, you can find out some such kind of similar situation in the past, synoptic situation. And when those situations were met, what was the rainfall? Finally, what was the rainfall distribution? So you can find out analog similarities from the past data and try to project it. Unfortunately, the analog doesn't really work well. Analog doesn't work well because from the same synoptic setting, you can get two different results depending upon, because it's highly nonlinear. The whole weather and weather prediction is highly nonlinear. Even though you may have the same kind of situation, but the final product can be different. So some people use it analog way, but it is not really useful. Only another is a time series. If you assume that there is a beautiful cycle, a 2-year cycle or 3-year cycle, unfortunately in meteorology, in weather and climate, we don't have a cycle. If you had a cycle, it would have been easy to predict. So, but we don't have a cycle. Then third is statistical methods. We use extensively statistical methods, especially for seasonal forecast, monsoon rainfall forecast. I will be talking about the seasonal forecast. The dynamical method is the most powerful tools, which we all extensively use everywhere. Very powerful tool and improved substantially, and still there are some gray areas. Then the latest emerging area is the AML methods. Huh?
There are cycles. The monsoon is a cyclical phenomenon. Temperatures are cyclic.
Pardon?
So there are cycles because many of the phenomena do have an underlying cyclicity. Monsoons come roughly at the same time every year. You won't capture small-scale fluctuations or extreme events, but at least there is some information in the cycle.
So I'll tell you. Many people ask me what do you know, how good your forecast is. I normally, as a lighter vein, I normally say, I know monsoon will come by May and it will go by October. This is well known. This I can easily predict. Remaining is I don't know. So we can tell monsoon is coming and monsoon is going. But even monsoon coming, onset, you say, there's a lot of variation. There's almost 10 days of variation, 10 to 15 days of variation. It can come on 1st June, it can come on 25th May, it can come on 10th of July, it can even come off some, latest onset was 18th June in 1972. 18th June it came, almost 18 days after that. So even though we know monsoon is going to come, what we know very, very confidently say monsoon will come. That we are very confident. Will come and go. But beyond that, I think there is a lot of fluctuations. Okay, so question of forecasting. Different kinds of forecasts we do. We start from nowcasting. Now that means basically forecasting next few hours, what will happen next 2 to 3 hours. And basically it is used for thunderstorm, lightning, flash flood, etc. Then we also have a small range called very short range, hours to 1 day. We can tell that also again thunderstorms, lightning, flash floods. Short to medium range forecast is the main weapon where we use for, especially for informing people in agriculture and water resources management. For them, the forecast up to 10 days is very important. 3 to 10 days is very important. So basically, we issue forecasts on rainfall, tropical cyclone, heat and cold waves, heavy precipitation, snowfall, etc. comes in here. So, and then extended range forecast is a new emerging area where we are doing a lot of research, whether we can predict next to 10 to 30 days. That's a period where we want to issue forecast. It's basically active and break phases, which I just mentioned about it. And this is extensively used for farmers. And then the seasonal up to 1 season before, so monsoon rainfall and El Nino, this prediction comes under seasonal prediction. There's also a new emerging area, which I will mention about, is annual to decadal. So for example, the climate change projection, which Krishna was talking about, 2070 what will happen, 2100 what will, that's what IPCC people are saying. What is the use of saying by 2100, monsoon will be like this, or heavy rainfall will be like frequency of heavy rainfall? No practical use. I mean to say that even for adaptation, 2100 is too far, too far. For the government, for Modi Saab, for Narendra Modi Saab, Prime Minister, Honorable Prime Minister, he will ask what will happen after 2 years. Because he can take a decision, he can, in terms of economic policies, in terms of development policy, investment, for some investment. If we tell him that after beyond 2 years and up to 5 years, monsoon rainfall is going to be very bad. We'll have 2-3 droughts. So be very useful information for him, isn't it? So that's a new area which is emerging is annual to decadal. Next 1 year to 10 years. So that is an emerging area. And climate change projections, which Dr. Krishnan was talking about. And very important thing, this is very important information. In weather systems, different weather systems have different spatial scale as well as temporal scale. For example, a dust devil will have a small spatial dimension. It's about 10 meters. Okay, a tornado will have about 100 meters, and a cumulus cloud will have 100 meter to less than 500 meters. A mesocyclone will have about this cycle. Severe thunderstorm will have this much cycle. Sea breeze will breeze. So you can have different time scales, different synoptic situations. Weather system have different spatial scale. And the time scale also it goes like this. For example, dust devil is a few minutes. It will last for a few minutes. Thunderstorm, for example, it will be a few hours. It will as thunderstorm forms, it will dissipate in 2-3 hours. Whereas so tropical cyclone, for example, it is a very large scale, 1,000 kilometers, and it can last about few days. It can even go up to 1 week to 10 days. So if the spatial dimension is more, the temporal dimension also is becoming more. Okay, then question comes, if you understand the spatial and temporal dimension, you can also predict in different way. For example, a tropical dust devil, you cannot predict in 1 week before or 10 days before. You cannot predict. Because the time span is small. Even thunderstorm, it's a small dimension in both temporally as well as spatially. So you cannot predict in 1 week before. A cyclone, you can predict 1 week before. Monsoon is monsoon is a planetary scale, 10,000s of kilometers. So that you can predict even 1 season before. So that's why many people ask, can you predict Sonipet weather? For example, what will happen on 12th of December over Sonipet? Can you tell now? Answer is no, you cannot do. You cannot do. People tell, still model can give you answer, but there is no predictability, there is no value. You cannot really do. So, but you can tell December, there is a probability of above normal rainfall, temperature over Sonipet in December 2020. That you can tell. But exactly whether it will be 23 degree or 12 degree is very difficult to say. So this differentiation you should always keep in mind. You should, once you try to predict it, you should know what you are predicting, what's its spatial dimension and what's its temporal dimension. Both you should know. So depending upon the nature of forecast, the models which you use also will be different. The models which you are using for tropical cyclone cannot be used for models for thunderstorms, predicting thunderstorm. So this differentiation is very, very important. We should understand. If you really want to do forecast, if you want to just listen to the forecast, then it's fine. If you really want to do forecast, then you should know this dimension. And so these are all forecasts. As well, the forecasts are given in different time scale. It starts from minutes. You can tell next few minutes. You can start in hours, days, 1 week, 2 weeks, 3 weeks, season, years, decades, centuries, etc. So it has a different application. The forecast in 1 week will have different application. And what it is used, what is the forecast value? If it is a few hours, we will say watches. Then we can also use for threat assessments. And if it is a long time, we can use it outlook. So monsoon prediction, we call as a monsoon outlook. For example, what will happen for during monsoon season. So it is given to the government to understand that what is going to happen this monsoon season. It's a kind of outlook. So exactly it may not really happen, but you will have a broader idea what will happen. So the forecast applications also different, and also how it is used for different purposes. Okay. And so the morning, I think Gautam, you are asking about what's the role of oceans. So this is the time scale for different aspects of Earth system. Atmosphere can have a memory only a few days. So if you really want to predict a 1 month, atmosphere will not help. Because after a few days, atmosphere will forget where you started. Okay, but if you want to predict for next 5 days, 6 days, atmosphere is enough. Ocean doesn't have a role. So you need not have a coupled model. You need only atmospheric model. But if you want to predict in a seasonal time scale, for example, next 1 season, ocean comes very important role. The ocean, in a day-to-day time scale, the ocean doesn't really change. The temperature of 25 degrees, tomorrow also it will be 25. But over land, over atmosphere, temperature can change from one day to day. So the day-to-day variability over atmosphere is very high, but it has a memory only a few days. So if you want to predict a longer time scale, you need ocean. And some people use a mixed layer of 100 meters or so. Some people use deep ocean, going up to 4,500 meters. But nowadays, all coupled models have very deep ocean models, ocean coupled. Not good as atmosphere. Not good as atmosphere. Is it happening? It's happening. There's a new instrument, for example, where MoES is investing a lot. It's called Argo floats. Argo floats. We send balloons. Many people have seen that over land we send balloons and take observation of temperature and humidity. Similarly, for atmosphere, for ocean, it's the temperature and salinity, not humidity. Salinity. How much salt content? That's very important because salt content, the salinity plays an important role of ocean circulation, like a density in the atmosphere. So salinity plays an important role. So it's a float. It goes down up to 1 kilometer, then comes back. Yeah, while going down, it takes observation. So it's floating in the ocean. It goes down, and then after reaching 1 kilometer, it comes up. We have, over Indian Ocean, we have put more than 300 now. But it has a lifetime of very few days. After a few days, it dies. Replacing. It's very costly. Very costly. And it's not made in India, so we import it. Over the ocean basins. All the whole Indian Ocean. We don't have specified area where we can keep. So, and also we have fixed data buoys. So this is almost like anchored. So then we have called drifting buoys. Simply put it there, it goes on drifting with the ocean current, and wherever it goes, it takes observation and send it to the satellite and comes back. So the new revolution is actually Argo floats. It gives you a lot of importance. So what ocean not only temperature, we also need a vertical profile. Like atmosphere, we need a vertical profile of temperature, humidity. We also know to know. So once Argo floats came, the skill of ocean forecast has improved substantially. Huge. But India is responsible for Indian Ocean, but all other countries are putting. So the whole tropics, I don't have a map to show you, but I can find out if you want. So beautiful data set. So ocean data is getting increasing a lot and it's making a lot of revolution.
Do we have enough information for the deep
So this only, it goes only up to 1 kilometer. Conveyor belt is still deeper. Still deeper. And satellite, unfortunately, cannot see beyond surface skin. Satellite can measure only the skin. Ocean is very, very peculiar. Electromagnetic wave doesn't propagate through water, ocean water. So if you really want any measurement, you have to use acoustic waves. Acoustic, sound waves. Electromagnetic waves doesn't flow. For example, light, it goes beyond 10 meters, it gets dissipated. You cannot penetrate below. Whereas atmosphere you can use, microwave, different kinds of electromagnetic radio spectrum you can use it. But in the ocean you cannot use it, unfortunately. So we use, for everything we use acoustic waves. And investments are very high. Ocean investment is very high.
You don't put like a station or something inside the
That also I said there are data buoys which are fixed location. It's a tied to the surface. Surface, it doesn't flow. So we have about, I don't know, about 18 or 20. No, they have been around for last 8-10 years. Available, yeah. Yeah. It's our institute in Hyderabad archives the ocean data. Okay. So if you really want to go for years together, then you need a deep ocean. And if you want daily 1,000 years, you need ice sheets, etc. So this is the way we work. And different kinds of model, as I said, we have a turbulence model, it's called large-scale ED model, which we use. But meteorologists, we don't use it extensively. We start from cloud resolving models, about 1 kilometer resolution models. And now casting thunderstorm, we have a mesoscale model, a model called WRF, I don't know how many, some of you must be knowing, weather and research forecasting model. It's a very popular model and it's freely available. Anybody can download it and run it on your PC. It's a beautiful model and it's about 3 to 10 kilometer. And global atmospheric model so what I said is that if you really want to predict a longer time scale, if you want to predict a bigger system, weather systems, you need a global model. You cannot use a regional model to use it. Okay, but if you want to predict only thunderstorm, heavy rains, or heat waves, etc., you can use this mesoscale model. So, but for climate time scale, you need a coupled ocean atmospheric model. Then Krishna was talking about air system model. That is the final, so where we use it for climate change scenarios. And this is a very different kinds of models, grid size and time, model domain size, etc. So as I said that Krishna also was talking, the numerical weather prediction started from Richardson, and he used many people to solve the equations. And as I said, he did not filter out the sound waves and gravity waves. That's why his calculations, he spent about 6-hour prediction he made with so many people involving, but the forecast was so bad. So because he did not filter out. And he assumed that in future, he never thought about computer. So he thought that in future, there can be a big factories producing weather forecasts. So this is the cartoon which many people put it, what Richardson thought about is in his mind. But he thought weather prediction is possible. And this is basically this person, Julie Grigor Charney. He was in MIT. He is the person who really is a Jew from Europe. This is the first paper. This is the first paper on numerical weather prediction. It was published in a Swedish journal called TELUS in 1950, 10 years before I was born. And this is the equation he solved. It's basically a barotropic vorticity equation. It's time derivative of vorticity. And you must have heard about this von Neumann. So he used a computer called ENIAC. This is the ENIAC. And this computer is completing 75 years now, this year. And it was able to do 5,000 additions per second, 5,000 additions per second. Now it is in peta, and people are talking about even exascale, 10 power 15 or 18. And this is a latest modern supercomputer which we use it in our countries. It's speed of petaflop. IITM, where Krishna is director, is a petaflop about a 10 petaflop, and now they are upgrading into 24 now. And this is how NWB system works. You start from data. So NWB is nothing but an initial value problem. You prescribe initial value condition, initial data, and run the equations. Basically, it's a partial differential equation. Solve it, integrate it with the forward type. That's the basic fundamental principle of NWP. So whether it is for weather prediction or even for climate prediction, the concept is same.
Does the world follow this?
Whole world follows it.
I meant the planet. If the initial conditions were known to me, will I know how the planet will evolve, or will it be more stochastic?
I could not follow.
No,
No, you have initial conditions of the three-dimensional initial condition.
actual planet,
Ah,
if I knew the initial conditions,
ah.
will I know how the planet's weather will evolve, or will it be more stochastic in the real world?
We can predict it using the equations, fundamental equations.
But will the real world be that?
Yes, 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 it should be. It should be. Theoretically, it should be. Because we use the equations of conservation of mass, energy, and momentum. Yeah, it's a basic principles. The same principles are used for astronomy people. For example, they will say after 1,000 years, this star will move from here to here. A meteor will come from here to here. How they predict it? It's the same physical systems. Only thing is, our atmospheric physical systems are chaotic. It's a course.
Now, do people try to put some noise also in this model?
Yes, sir. Yes, sir. Uncertainty, you cannot introduce it, but model forecast has, because initial conditions are not perfect. Whatever observations you take, initial conditions are not perfect. Okay. So the error in the initial condition, I will talk about that. The initial condition have an error. That error will go on growing.
So only stochasticity is in the initial condition.
Initially, because it's a partial differential equation, you can solve it only if you know the t is equal to 0.
No, but what you're saying is that partial differential equations describe the world better than stochastic differential equations.
Yes. Yes.
Ask a similar question. That do we know that these equations don't have chaotic solutions?
Yeah, we don't know.
So short-term prediction is okay, but maybe longer term may be problematic.
So I will tell you, so for longer time what we do is we don't use deterministic forecast. We use again stochastic forecast. We prepare, using the same equation, we prepare a scenario of forecast. Okay, we call ensembles, different scenario. From different scenarios you can calculate how much probability is this.
But there the stochasticity is in the,
Stochastic comes under.
the initial condition.
Yes,
in
yes,
the
yes.
ensemble of initial
Yes, when we do ensemble, the initial conditions are not perfect. So to take care of the uncertainty in the initial condition, we perturb the initial condition here and there. For example, temperature is over is 12.5. It can be 12.56. It can be 12.48. Okay, small error. And this small error is good enough for giving uncertainty in the forecast. So we perturb the initial conditions. There are many ways of perturbing the initial condition. Now sophisticated methods have come. And so you perturb the initial condition, you prepare many forecasts. So if you have a big computer, you can run hundreds of ensembles. What we do now is 20 ensembles, sometimes 40 ensembles. So once you have an ensemble forecast, then you can prepare basically the stochastic framework.
But the faith is that the ensemble will stabilize in probabilistic sense.
Yes.
It's not going to be like if I took 1,000.
Yes. Yeah. The question is how many ensembles you need? How many ensemble members do you need a perfect solution? Is it this one?
Like with 1,000 I get one answer, with 10,000 I get a completely different answer.
Yes.
It's not that, right?
Yes. Yes.
Yeah, there's some periodicity to it.
Yes. Yes. Okay. So I'll move on. So you start from an initial condition, then you have a model. Model has assimilation, then it's a part of dynamics part. Then by dynamics nothing but equations. Then you solve. You have physics. Then you can post-process it. In the post-processing also nowadays many ML methods are being used. For example, model doesn't give you a thunderstorm in the model. Model gives you temperature, humidity, wind speed, etc. You have to convert it into a forecast for thunderstorm. Okay. So a good forecaster who has a lot of experience can, by seeing these parameters, can say that thunderstorm is going to happen. But it may not be an objective way of doing it. So if you really want to do it, you can use this model forecast to predict a thunderstorm. So ML methods are essentially used for post-processing of the data. The post-processing of the model output. So the forecaster in IMD, for example, don't use the raw NWP forecast for issuing forecast. Okay. Either they apply their own knowledge that comes with the experience, or they use this kind of methods. Okay, so now where are the data? How you get the data? These are the data. You have plenty of data available. It's called, we have satellites. Satellites also, you have polar orbiting satellites, you have geostationary satellites, and you have high altitude research aircraft, which you are talking about, even commercial aircrafts, which you have, when we are flying, pilots will be taking observations. So there's an instrument for the temperature, humidity, everything, and that data observations goes into a surface, into a kind of metaphase on a relay mode. And we have ships Wherever ships also goes, wherever it goes, they take observations. And they send it to the radio station nearby. And we have, it's called drifting buoys. We have, it's called, we have pilot radio sonde going up. We have radars. And we have aircraft, piloted aircraft. And we have, now we are using drones. We use extensively drones for taking observations. So we have plenty of observations. And we have typical observatories maintained by meteorological offices by all the country. And we have a beautiful system. All these observations all are controlled by a system called, by an organization called World Meteorological Organization. It is similar like World Health Organization. It's a UN organization with the headquarters in Geneva. I'm an expert member for the WMO Research Board. So only collaboration among all countries happens only under this WMO umbrella. For example, we have good understanding with Pakistan. Pakistan data comes to us. Our data goes to Pakistan. There's no conflict because we all know the weather cannot differentiate the countries, the boundaries. Okay, so there's a beautiful understanding. Only, I think WMO should get the Nobel Prize for Peace because there is an organization bringing all people together. So when we go for the meeting, all countries come together, Iran, Iraq, no differentiation, because they all need our data and we also need their data. And all these surface observatories were, the typical meteorological observatories, they take observations fixed time throughout the world. We follow a time called universal coordinated time. This is nothing but GMT, UTC we call it. 0 UTC is morning 5:30 here, morning 5:30. So morning 5:30, whole world will taking observations together, surface observation. And we exchange it through our telecommunication system. Then next observation will be at 3, 8, so every 3 hours we take observations.
Is that some kind of data assimilation?
Yeah, so that's why then all the data, for example, NCMRW of Noida get all this data through IMD, and they archive this, and they first of all, they do a quality control because all the data may not be good. So we have a protocol for quality control, and once you do the quality control, once the qualified data goes into assimilation.
It's kind of a interpolation exercise.
Data assimilation, nothing but, finally, if you want to, the equations, if you really want to solve it using finite difference, you need at a gridded point, isn't it? Fixed grid. The observations are sporadic, isn't it? It's not in a regular grid. So we need to interpolate into a regular grid, and this data should be consistent physically. Physics-wise, it should be consistent. Okay.
It's kind of a mathematical.
Yeah, we use a method called ensemble-Kalman filter. Ensemble-Kalman filter. That's a method we use it for data assimilation.
So I guess my question is, maybe there are a variety of different ways of doing this.
So data assimilation is entirely a different ball game.
So that's my question.
I say that people can talk about hours together.
But do we have enough expertise?
We have. No, I'm not an expert, but we have expertise in India. Yeah, we are well trained. But there is a lot of scope for improvement. So people are working on that. And also a new method. See, now if you are a coupled model, the atmosphere model will be assimilated separately with atmospheric data. Ocean will be assimilated separately with ocean data. That was earlier, it was going on, even now. But that gives a lot of differences because ocean energy is fed into the atmosphere. And atmosphere energy is fed into, for example, atmosphere wind drives the ocean circulation, isn't it? And for example, latent heat flux or sensible heat flux is driven by atmosphere. So this both should be consistent with each other. So when you do the assimilation differently, there is a mismatch. So now a new concept called coupled data assimilation. So you data assimilate, put it together, and do it together so that all this ocean and atmosphere comes together, consistently each other. It should be.
Yeah, because ensemble, Kalman filtering is just kind of least squares optimization, right?
Exactly, that's the same
But
thing.
there are a variety of other ways of doing optimization.
There could be. You can really contribute if you have.
That's what I'm saying, but is there maybe you want to discuss these things more?
I think you should, people in NCMRWF, there's two groups are working on that. And, but they don't do basic research. Basic research they don't. No, they don't do. So they don't do it. They apply known methods and they use it, that's all.
Those methods are being developed in
Developed in outside. Europe, Basically, the European Center for Medium Range Weather Forecasting, that's in UK. So that's a center where all this data assimilation research is done, basic research. They do extensive research. There is a joke. When you go, if you go with NCMRW with a pen drive, they will make sure that all the data in the pen drive are taken by them and they put it into the model. So they say that you don't take any pen drive into the. That what literally means they use all kind of data. They don't throw out any data. They show even one data. They ensure that it goes into the model because the ultimate aim is to make the initial conditions perfect. How much data can go inside if they make it? And if we want few data, even a small satellite data, if it doesn't fit into, they change their data assimilation package so that this data also is assimilated.
Are they using less data for India and maybe they were
No. They are the people who use maximum number of observations into the model.
maybe India is collecting less data, so they're giving them less data?
No. There is no selection. So I asked the same question. For example, the initial condition prepared by ECMWF and the initial condition prepared by NCMRWF, there are differences. Same day. I asked the question, how can this be different? Then they say that they use some data which are not available to them. They use more data which are not available to. I asked what are the data, but they have some countries, especially satellite data. China, for example. They have satellite data which are not available to us, but they are available to ECMWF. So if we use 80% of data, for example, if they use 100% of data for assimilation, we may be using about 85, 90. We use less number of observations than ECMWF. So obviously the difference will be there.
For example, we have less radars for preparation.
But this same radar data goes to them only.
No, I know, but because we're giving less and Europe is giving more, they have a better fit for Europe than they have for India.
And that kind of things are not happening. Once you put in the data doesn't understand from where it came, from whether it came from Europe or India. So data is data. You mean to say that data rejection, you mean to say? So that if there are less number of observations from one region, the data quality over that region will be poor.
That's all.
Yeah, that's poor. That I agree.
No, I'm basing this on the fact that the precipitation forecast of these SRDS monsoon they are not very good.
Yes.
I'm basing it on the fact that maybe they don't get inputs very well.
Yes. Quite possible. Okay, so I will move on. And so these are kind of observations which we make. So you are talking about the aircraft. This is the aircraft. You can see that over transatlantic, there is a beautiful observations from Europe to US. And here we don't get much observation. Over Indian region, we get some. This is a radio zone. This is a surface observation. As I said that wherever land is there, we take observation, and wherever oceans are there. And these are all satellite data. There are plenty of satellite data. If you assume that the 100 data goes into the data assimilation, 90 data comes from satellites. So satellite is the main inputs for data assimilation. And another interesting point is if 100 data are from satellites, only 80% of data goes into data assimilation. Remaining all data goes into rejection. Even satellite data, because they do a quality control. So when the quality control, even satellite data is a huge number of volume of data, it doesn't really go all the data into the model. So the emphasis is on improving the satellite data quality. So there the algorithms of deriving temperature, humidity, etc. So there is a lot of research is going on in satellite, we call satellite meteorology, where the satellite sensors are, how the satellite information can be used to derive better products. Okay, so these are different satellites we use for Earth system observation. You can see that's a huge number of satellites. And this is the basic equations that the morning also Krishna was talking about. This is the momentum equation in U, V. Wind can be divided into a horizontal component, two winds, U and V, and there's a vertical component, okay, U, V, W. And this is for U, this is for V, and this is for W. And this is the continuity equation. And so this is nothing but F is equal to Ma. Nothing but F is equal to Ma. Okay. And so that's why I put the Newton's photo here. So du by dt. So in this is the coriolis force. This is the pressure gradient force. So in the x direction, the pressure gradient force is the main driving force of the wind. In the Vertical velocity, there is no pressure gradient. It's only the pressure difference in the height. And so if you really do the scale analysis of these three equations, the third equation, the dW by dt will be 0, because the value of vertical velocity in a typical atmosphere is very small. The horizontal wind speed could be 10 meter per second, 20 meter per second. For cyclone, it will be 30, 40 meter per second. Whereas vertical velocity will be 10 centimeter, 2 millimeter per second. So in general atmosphere, stable atmosphere, vertical velocity is small. So this parameter, this value, this can be put as a 0. So basically there's a balance between this term and this G. So that's why we call the atmosphere and general atmosphere is a hydrostatic balance. But this hydrostatic balance will not be there for a thunderstorm. When thunderstorm happen, there will be large vertical velocity. You can even have to go to 15 meter per second. So then this equation, this part is become very important. So then generally the models are hydrostatic balance models. So this equation will be only last part, only these two terms will be there. But for the thunderstorm prediction, the models are non-hydrostatic models. For example, WRF model which they use, the models are non-hydrostatic models. So if you really want to predict thunderstorm, don't use a hydrostatic model because the basic concept is wrong. And this is the continuity equation. This is the conservation of energy. It's basically the thermodynamics. And this is the famous gas law. This is the water vapor. For the for the ocean also, the equations are almost similar. So instead of here, the main difference is ocean is not compressible. You cannot compress water. So there's an incompressible equations for incompressible fluid. That's all difference. And also there is a tracer conservation, nothing but is a salinity. There will be an equation separately for a salinity. Okay. And so basically the equation, how you do it, you start with the initial condition and you use the forcing and multiply by delta time, you get a new forecast. This is
technical question. Even for the air, if you use an incompressible approximation, the speed of sound in air is much larger than the speeds that you were talking about. Is that normally done?
we don't do. So you mean to say that the atmosphere can be considered as incompressible fluid?
Because the usual thing is if velocity's ratio of normal velocity to speed of sound is much smaller than 1.
Here the sound waves are not at all taken care. Sound waves are filtered out. Sound and gravity waves are filtered out. Then only you can get the meteorological waves.
So I wanted to ask, why is that? You mentioned that earlier.
Because speeds are different. Speeds are different.
So if you put them in, then you will get wrong answers.
So Richardson did the same thing. He did not filter out. So we do the way the equation when solving it. First you filter out the sound waves by doing some approximation and filter out the gravity waves. Then you further you solve it. Then so meteorological waves will be retained. Remaining all waves will be. Because we are not worried about sound waves. Okay.
So in this equation, the delta T that you have, how many, this is a global level you're doing, right?
Pardon? This is for at every grid point you can do this. You know the initial condition.
Yeah. All the calculations are going on at each grid point?
Oh, plenty. It's a four-dimensional. So I'll tell you how much it will be. Huge calculations.
So per grid, is it millions of calculations?
Yes.
And the grid points themselves also.
Yes. Depending upon how much is the resolution of the model. We use 12 kilometer. Now we are moving into 5 kilometer model. And vertically, we use 64 levels, vertical velocity.
No, but that will increase the grid point.
Yes.
But per grid point, how much calculation?
Per grid point, so many calculations. Depending upon how much you want to forecast. For example, how many days? If you want to predict only 2 days, it's fine. Only a few calculations. And there is a relationship between delta T, delta X. In the numerical method, there is a different relation between delta X and delta T. You cannot use any delta T for any delta X. There's a relation. It's called CFL criteria for numerical methods, finite difference methods. CFL. C is the velocity of the meteorological wave which we are producing. C delta X by delta T should be less than 1. So the meaning is if your delta X is small, that means your resolution is small, resolution is high, for example 1 kilometer, delta T can be small. Few seconds, few millimeters. So that means you can get more forecast. So that's the meaning. So these are all related. And so we use two methods. One is time derivative is basically finite difference method. Spatial derivative, there are many options. One is finite difference. Another is spectral methods. So spectral methods are now extensively used instead of finite difference. And NWP, finite difference and spectral methods are generally used for discrete equation. So this is the way Krishna was showing that this is the models. The whole globe can be divided into different grids. And each grid, their calculation should be done. And also there is a advection, so there is each different grids are also connected, interconnected. Okay, it's not very independent. Okay, there's a lot of advection time comes. And this is the ECMW of vertical level. You can see how many levels it has. It has about 137 levels. And the distance between two levels over the upper atmosphere is much coarser. But if you come very close, it will be very narrow. Every 10 meter, every 20 meter, there will be one level. And this is a new grid has come. It's a octahedral grid. It's a new concept. It's ECMWF again. And in India also, IIT Pune has done this grid. This is, I don't know much about it, but then they say that it can solve, it can really give much more better results than LDO. You can see each grid, it's not a square. You can see that it's a kind of a triangle kind of thing. And we had in the earlier grid, if you really use the Cartesian grid, then we have a problem over the poles. It's not the same. The area here and the area here is different. So we had issues. So this will solve that kind of problem. And IITM has so this is the data assimilation which I told. And the model also has a physics. The thermodynamic equation, if you really saw, you said there's a physics term called diabatic heating term, diabatic heating. Nothing but radiation, clouds, planetary boundary layer process, land surface process. This all involves physics. And these are the different kinds of physics which you use for parameterizing in the model. For example, how the short wave solar radiation is coming and how is getting reflected by clouds and aerosols. And there is also long wave radiation going up through different gases. Then there's a convection, shallow convection, deep convection, big cloud, then precipitation, wind waves. Then over the orography, there will be a drag. It's called orography drag. When wind flows over the mountain region, we get so-called orographic wave drag. And we have turbulent diffusion. Then there's a lot of chemistry. We have ocean. We have surface. So many things. So we have to use it different physics. So then a cloud, as I said, if you use a 50-kilometer model, the cloud is only a 5 kilometer. Okay, so the cloud is within the 50-kilometer model. So how we treat the cloud, you have to use indirect way of treating the cloud. So you cannot explicitly use it. So that's what we call parameterization. We have to use cloud as a parameter. You have to use within the grid, 50-kilometer grid, how the cloud forms, how the condensation process, and how cloud grow. And once the condensation process, it releases latent heat. It basically heats up the atmosphere. It's basically energy, and that energy is driving the atmosphere. Okay, so we need to really treat. And the basic problem in our future, I will be talking about is this cloud parameterization. We are very poor. The models do very poorly the cloud parameterization. We don't know much about clouds. Mainly, one of the reasons is clouds are in the sky. If it is somewhere down, we could have brought the cloud into the lab and we could have done it. We cannot do it. So we have observations, aircraft going into the clouds and taking observations. So we cannot do an experiment with the natural clouds. That's a problem. And this is how the rain process. So I will brief about this, so you will understand how difficult to make a prediction for rain. So rain process, this is the rain process. And how much is involved with, you can see that how many processes are involved to get a prediction of rain. There is a cloud water, then there is a process called autoconversion, and how this accretion is happening. Some hail will forming, and hail can really give rise to rain, freezing, melting. So much complex process. But we know this process not in very detail. We know very well. It's all basically it's a cloud physics. We understand it, but there could be a lot of errors in this. So if you make any small mistakes in making, for example, autoconversion, that will lead to a forecast error. Understood? So this is the area where AML, if you use it, you don't understand what the autoconversion, you don't worry about what autoconversion is. Okay. So this is the area where you can AML methods will succeed where physics doesn't really work very well. We don't know much about physics. These are the two areas. This is the place where AML methods can work. And this is the butterfly effect which Lawrence, which Krishnan also was talking. So he is from MIT. He tried to solve an equation, three equations. And so he started with initial condition. One is 76.8 and is 76.853. Okay. And you see how the final output is going. After a few hours, it's completely diverging. So then that is the time he told that our forecast, especially weather forecast, because partial differential equations is very sensitive to the initial condition. So if we assume whatever observations you use it, still there could be errors. So this is the equation, three equation he used it, and this is the way he got it. So this is so you start from one initial condition, but after a few hours, one can go to this regime, another can go to this regime, different regime. And this looks like a butterfly, isn't it? That's why we call it butterfly effect. So any small perturbation in New York can cause a big heavy rain in Japan. That's a butterfly effect, people say. Okay, so his concept is that our forecasts are very sensitive to the initial conditions. So you have to be perfect with the initial condition. So there is a chaotic element comes in the atmosphere. And that's why we use ensemble forecast. So you start with one initial condition and produce one forecast. This is a deterministic forecast, we say. Just a forecast for one value up to 10 days, then you can get one value. But then you can also, initial conditions, you can perturb it, and you can have a scenario of a forecast. Then you can get a broader spectrum of a forecast, and that can be used to calculate the probabilities. So that is the method which now people follow it. So deterministic forecast is good for next 2 to 3 days. Beyond 3 days, it should be all stochastic forecast. That's what our concept now. So for any forecast beyond 3 days or 5 days, we use deterministic stochastic forecast. This one? No, how many, for example, this is a probability of precipitation present day. How many, say for example, you have 30 ensembles. From 30 ensembles, what is the probability of for different category, rainfall category? One model will be predicting 2 centimeter. Another model will be predicting 5 centimeter. Understood? So each grid point, you can calculate what is the probability of 2 centimeter and 5 centimeter, and then you can plot it. So if the probability is high, that means you have more confidence that will happen. So I will give an example. This, I don't know, the picture is not so good. This is the way we use seasonal forecast using ensemble methods. We run some 30 ensembles, and we calculate below normal category, above normal category, and use this. This is for the forecast for this year. You can see that every year, most of the places is all above normal. The model is predicting high probability for above normal. Above normal means the whole monsoon rainfall you divide it into 3. We call tercile. And first 33% is above normal, middle is normal, bottom 33% is below normal. So from model forecast, you can calculate what is the probability for above normal, normal, and below normal. So this is the information which we give to the government. Okay. So we have, so people here can understand that the model is predicting, IMD is predicting above normal rainfall during this season. And also the predictability, important is forecast skill. As I told that atmosphere starts with initial condition, but rapidly it falls. So initially the short range forecast, it goes good for 1 day, but it drops sharply after 3 days, 4 to 5 days. Over the middle latitudes, over Europe and US, this graph may go a little this way and drops. Whereas in India, this may drop very quickly. That's the difference between, that's why people ask, oh, in the US forecast it's not good, but in the US people are predicting better. Because the weather systems in US is different from weather systems over India. Okay, so they are not very sensitive to initial condition, whereas other weather systems are much more sensitive to the initial conditions. Okay, so then there is a small predictability comes in extended time scale, the small predictability comes in. a seasonal time scale. So this, we have started a monsoon mission in 2012 to improve our monsoon forecast. And this is the, again, the forecast, sorry, the diagram which, sorry, the slide which Krishna was showing, that how the forecasts have improved for the last 30 years. So you can a substantial improvement. As I said, the southern hemisphere has improved because observations have started coming after 2000. And now the 5-day forecast earlier is now is equivalent to 7-day forecast, or 3-day forecast in 80 is equivalent to 7-day forecast. So we have improved substantially. But so for last 30, 40 years of doing the intensive research and observations, putting more observation, improving models, we could improve forecast by 2 to 3 days. That's all it happened. You can understand how bad our situation is, how difficult our situation is. So we could improve last 30 years, only 2 days or 3 days forecast.
These are now exact forecasts.
These are deterministic forecasts. This is basically 500 millibar geopotential height. 500 millibar is about 5.6 kilometer. What is the height of that from the surface? So we call geopotential height. And you can also very interesting is the 3-day forecast is almost like a flat. It doesn't really is improving. So whatever skill we have, it's not improving. But what is improving is the forecast in the longer time scale. That is mainly because observations have improved. So with the new data, initial conditions have improved. So it is going beyond the chaotic the limit, the predictability limit. Yeah, physics also improved. We know the cloud process, etc., very far better than that area. This is the last, I think this is the last one I will be showing in this presentation. These are 4 maps. One is observation, remaining all model. Can you differentiate which one is observations, which one is model? One is observations and remaining all are models. All looks very similar, isn't it? That is the beauty of our present NWP models. This is the observations. This is satellite observations. This is a model at 1.4 kilometer solution. 1.4. This is a model at 9 kilometer. This is the model 9 kilometer, but it is in different, without deep convection. So we have, for last many years, we have improved a lot numerical weather prediction. Still, we have a lot of gray areas, which I will be talking in the next one. Can I start now, or can I take a break? I'll make a 5 minutes break, then we'll start. That's only one last part. You should stop for what time?
Well, we have time to stop at 6:10.
6:10. So then I will continue, I think. Can you help?
We can take a break. I will stop at 6:15.
It's okay? I will sit and